Hello together. In the last lecture we did discuss the unstable amplifier or an active device, and we did discuss under which circumstances the voltages U1 and U2 can exist without any voltage which we feed as a signal into our amplifier. And we found this equation that the admittance at the total admittance in the input must be zero, and also that the total admittance at the output must be zero, but both equations will be fulfilled at the same time. So what we do now is we will separate the generator admittance in its real part and its imaginary part, and the same we will do with the input admittance here in its real part and its imaginary part. And of course we have a complex valued equation, so in a complex valued equation where the total equation is zero, also the imaginary part must be zero and the real part itself must be zero. So in the case of the imaginary part it's quite easy. So for example, if the generator susceptance will be, for example, capacitive, then the input susceptance must be negative, or it will be inductive. And the same, of course, if this would be inductive, then this term would be capacitive. But in the case of a real generator admittance, we know that the generator admittance itself must be or will be always greater than zero, and if this equation shall hold true, then the small signal input conductance must become negative. And this is the first time you see here that the small signal input conductance can become negative. But the same considerations which we had here we can do also for the output, because both equations hold true in the same time. So again here, if we consider the imaginary part, then of course the susceptance of the output admittance, for example, must be negative, equal to the negative value. Again, if this is capacitive, this will be inductive and vice versa. But also for a load admittance at the output, we know that always the real part or the conductance will be greater than zero. This means again at the output there must be a negative small signal conductance. So in the case where we have a voltage here and a voltage at the output, we must see into the amplifier or into the active device always a small signal conductance. To go on in our consideration, we now have a look again to our configuration, and here I again sketched that we have here the input admittance and here the output admittance, and of course this input admittance will always be, for example, a function of the load admittance at the output. So this load admittance at the output will also influence the conductance I see into our two-port here. And we saw we have an unstable system as long as the input conductance is negative. So we can say if the input conductance here, which is a function of the load admittance, is always positive independent of the value of YL, then we will have a stable system. So as long as this equation holds true, independent of YL, then our system is stable. And the same considerations apply to the output. We can have here the output admittance, and of course the output admittance will now be a function of GL. And as long as it is negative, then it's unstable. But it will be stable if the output admittance is always positive, independent on the fact which generator admittance I have in the input. So to go on in our consideration, we have to have a more closer look to this equation. We see as long as the input conductance, the small signal input conductance, is greater than 0, independent of YL, then our configuration will be stable. And now we have a look to this equation in detail, and the first, on a first glance, we already see that the necessary condition is that G11 must be greater than 0. If this would be not the case, then of course it cannot be always greater than 0. So G11 must be greater than 0. So after a lot of mathematics, we end up in this equation here. And to make it easier to have a look to this equation, I insert some values, GCL here and VCL here. And then we end up in this equation, which you can recognize as an equation for the circle in the load plane. So we have here, in principle, x squared plus y squared is r squared. This would be normally the equation for a circle, and now this circle is shifted by this value in principle in the x direction, and by this value in the y direction. So what I did here, I sketched the load plane. The load plane is defined as, we have here the conductance of the load, and here we have the susceptance of the load. And these two values now define the center of our circle. And this value here defines the radius of the circle, OL. This is our radius of the circle, and we see as long as this term is greater than the circle, then we have a positive input conductance, which means we have a stable system. So as soon as our YL comes out of this circle, we have the problem that we have here, it's unstable. To summarize, now we found that the condition that the input conductance is positive leads us to the definition of a circle in the load plane, and as long as YL, which is a member of the load plane, is outside this circle, this will lead to a stable system, and as soon as the load admittance comes out of the circle, we end up in an unstable system. The same consideration we did in the load plane, we can also extend to the generator plane. In the generator plane, we can also define the output conductance, and of course, to be stable, it must be greater than 0, but it again is a function of the generator admittance. So again we find here the necessary condition that the output conductance can only be greater than 0 if already G22 is greater than 0. And if you apply all the mathematics again, then we end up again in a equation for a circle in the generator plane. And I defined here the center, the values of the center of the circle and the value of the radius of the circle. So the center in the G-plane is given by this, which means this point, this is the center of the circle in the direction of the conductance, and here we have the center in the direction of the subsistence, and inside, as soon as again the generator admittance comes inside, from inside the circle, then we end up in an unstable system, and as long as the generator admittance comes from outside the circle, then we have a stable system. And in the next lecture we will use the simulation tool to see how these circles also move in the planes, because the Y parameters, they are frequency dependent.